Let me begin by introducing our presentation. We will be presenting the fault-tolerant distributed payment processing system. This project focuses on designing a reliable and highly available payment system that continues to function even if some components fail. As a team, we concentrated on four main areas: fault tolerance and recovery, data replication and consistency, time synchronization, and consensus algorithms. With that brief introduction, let's move on to the main problem of our system addresses. Now let's look at the problem our system is designed to solve. In today's e-commerce environment, payments must be fast, secure, and continuously available. Even a minor failure can interrupt thousands of transactions and affect customer trust. Our main goal was to create a system that processes payments reliably with zero data loss even during network or server failures. To achieve this, we focused on preventing transaction loss, managing latency, maintaining strong data consistency, and ensuring 24/7 uptime. Next, I'll explain how our system architecture supports these goals. Let's take a look at the overall architecture of our system. It's built using a clustered design with multiple payment servers. A single leader node coordinates all write operations, while failover node replicates data to maintain reliability. MongoDB is used as the main storage layer to ensure durability and scalability. This setup helps distribute load evenly, remove single points of failure, and improve overall performance. Now let's move on to how our system handles failures and recovers automatically. We implemented proactive mechanisms to detect failures and recover automatically. Each node sends heartbeat signals even 2 seconds. If 3 are missed, the node is marked as down and a new leader is elected within about half a second. When the failed node returns, it synchronizes missed transactions before rejoining the cluster. These features allow the system to maintain around 99.9% uptime even under heavy stress conditions. That covers the fault tolerance aspects of our system. Now I'll hand over this presentation to Malidu.
Thank you, Shadi. This is my part. So, how we keep data safe and consistent. So, hello everyone. Let's talk about how our payment system works. We have a main server called the leader. When you make a payment, the leader sends that information to all other servers called followers. The leader waits until most of the followers says, "Okay, we got it." Only then does it finalize the payment and tell you it was successful. This is called a strong consistency. It means that once your payment is confirmed, anyone checking their account will see the new updated information right away. We also make sure you can't be charged twice. Every payment has a unique ID like a fingerprint. So if the same payment comes in again, we recognize the fingerprint and ignore it. And we can do all of this 1200 times every second. So next slide. uh, it's making sure events happen in the right order. Now here's a tricky problem. What if the clocks on our servers are a little bit different? How do we know which payment really happened first? If we get the order wrong, it causes problems. We fix this in two ways. First, we sync all the servers clocks with internet time server every minute. This makes sure all the clocks are very close to each other. Second, sometimes messages arrive in the wrong order. So we give each one a number, then we put them in the correct number order before we process them. By doing these two things, we are 100% sure that all transactions are processed in the perfect order. So next slide. How all servers agree. The Raft algorithm. So how do all the servers agree on what to do? We use something called the Raft algorithm. It's like the rule book of our servers. First, it picks a leader. If the leader stops working, the other servers quickly vote for a new one. This takes less than a half second. Second, it manages the data. The leader sends new data to the followers. The second data is only saved after most of the followers agree. System is very safe. Even if a network problem splits the servers into two groups, the rulebook prevents any confusion or conflicting data. So Next part, the whole payment journey. Let's walk through the entire life of a single payment. I'll show you how all the parts we just talked about work together. Step 1, you send a payment. It's all start when the customer click pay. Your phone or computer sends the payment request to our system. Step 2, the leader checks our duplicates. The request arrives to our leader server. The very first thing the leader does is look at the payment's unique ID. It checks its record to ask, have I seen this exact payment before? This is our duplicate protection in action. If it is a duplicate, we stop here. If it is a new, we move forward. Step 3, the leader adds timestamp. Now the leader gives the payment a timestamp, but this isn't just any time. It's super accurate synchronized time from our NTP system. This stamp ensures this payment will always be in the correct order in history, no matter what. Next step, sharing the payment with followers. Next, the leader uses the Raft rulebook. It packages the payment into a log entry and this sends this package to every single follower server. It's like the leader is saying, hey team, here's a new payment. I want us all to record. Next steps, finalizing and saving the payment, sending your confirmation. So from the moment you click pay to the moment you see that confirmation, you are protected by strong, consistent and self-healing system. This is the reliable engine that powers every transaction. So these are my parts. I will now hand over to Hasit. Thank you.
Our system is built using simple but powerful tech stack. We used Python 3.9 for main development because it's reliable and easy to work with. For backend, we used Fast API, which help handle client requests quickly and efficiently. It's lightweight and great building fast to REST APIs. For storing data, we used SQLite, which is simple, fast, and perfect for managing payment records in a distributed setup. The Rust the Raft Consensus Algorithm makes sure all the nodes agree on same data, even if some of them fail. We also included health monitoring and automatic node discovery. So if one node goes down, it can reconnect automatically once it back. Together, this setup keeps our payment system consistent, fast, and highly reliable. Then we moved on to the test to see how well system performs. It manages handle 1200 transactions per second, showing strong performance. Each transaction took only about 80 milliseconds to complete. When the main leader node fails, a new one was selected in just 420 milliseconds, so there was almost no downtime. Our clock synchronization accuracy was within minus plus 10 milliseconds, keeping all transactions in right order. In total, we tested 10,000 transactions and every single one was processed without errors or data loss. Even when we simulated crashes and network problems, the system continued to run smoothly and stayed consistent. Here's a quick summary of how well the system performed. It maintained 99% down uptime, meaning it was available almost all the time. It recovered from failure in under 500 milliseconds. There was zero data loss and all transactions were safely replicated. It kept up a rate of 1200 transactions per second with all data staying consistent, and time synchronization remained accurate within 10 milliseconds. These results prove that the system is fast, fault tolerant, and ready for real world use. And here are some challenges we faced and how we fixed them. One issue was multiple leaders forming during network problems, which could lead to confusion. We solve it using majority voting, so only one leader can be active at a time. Another problem was duplicate system when client retired after timeouts. We fixed by using unique transaction ID, make sure each payment processed only once. We also faced slow recovery times when a node restarted. To fix this, we added snapshot and incremental syncing, which help the nodes recover faster. Finally, clock drift between servers caused timing issues. We solved this using frequent NTP synchronization to keep all the system clocks accurate. After solving these challenges, our system became stable, fault tolerant, and ready for continuous payment processing.
Thank you, Hasit. So, throughout this project, we gained valuable insights into the real world challenges of building a highly resilient distributed payment infrastructure. One of the biggest lessons we learned is that testing distributed systems is hard. We can't just rely on traditional unit tests because distributed environments involve concurrency, timing issues, and partial failures. To test these systems effectively, we need sophisticated tooling that can accurately simulate real world network behavior and fault conditions. We also discovered that simulating real failures is not optional, it's essential. By integrating chaos engineering into the development lifecycle, we were able to uncover hidden edge cases that would have been impossible to detect through normal testings. These simulations helped us understand how the system behaves under stress and prepare us to recover from unexpected scenarios. Another important takeaway is that simple protocols often work best. By choosing well understood, proven consensus mechanisms, we reduced overall complexity and minimized potential bugs. This simplicity made our system not only easier to reason about but also more reliable in production. Team coordination was another critical factor. Distributed systems aren't just technically complex, they also demand strong collaboration, ensuring everyone on the team shared a clear understanding of how different components interact was key to avoiding miscommunication and design mismatches. Finally, monitoring and logging proved absolutely essential. Deep visibility into the system state and performance was critical for debugging and maintaining reliability. These observability tools helped us detect anomalies early and ensure smooth operation in production. Looking ahead, our focus is on scaling and production readiness. First, we plan to implement multi-data center deployment to achieve geographic redundancy. This will protect against regional outages and improve global availability, ensuring our payment system stays online even in the face of large-scale disruptions. Next, we are introducing horizontal sharding for scale. By distributing the database load across multiple shards, we can handle massive transaction volumes efficiently while maintaining low latency and high performance. We also aim to strengthen our security architecture with end-to-end encryption, strong authentication and authorization mechanisms, and dedicated key management services. These steps are critical for maintaining trust and compliance in financial systems. To improve operational visibility, we'll be developing advanced monitoring dashboards. These will provide both executing and engineering teams with real-time insights, enabling predictive alerting and faster incident response. Finally, we'll automate chaos testing as part of our continuous integration pipeline. This means regularly injecting control failures into the production-like environment to continuously validate our system's resilience assumptions. Our efforts have resulted in a fault-tolerant payment system designed to maintain service continuity even when components fail. In the event of a server failure, the system automatically performs failover, ensuring that clients' requests are handled seamlessly. We maintain strong consistency guarantees, meaning that every observer always sees the same data, a critical requirement for financial transactions. We achieved high availability, 99.9% uptime, minimizing downtime and ensuring uninterrupted payment processing for mission critical operations. And perhaps our proudest achievement, zero data loss. Through rigorous testing and robust consensus mechanisms, we successfully preserved all transaction data even during simulated severe network and node failures. Thank you. In closing, we are now ready to move to the multi-data center staging environment and begin integration testing. Our immediate next steps include reviewing and refining the sharding strategy, finalizing advanced security protocols, and scheduling the production rollout timeline. We are confident that these enhancements will take our system from a successful prototype to a truly production-ready, globally scalable payment infrastructure. Now, I'd be happy to take any questions or discuss the next steps for deployment and scaling. Yes, so now let's take a look at our distributed system here, our payment integration system. So first we will have to include the recipient ID, for example T200, and then we have to include our amount of transactions, and then we have to process the transaction. Once the transaction is done, we will get a pop-up saying the transaction is successful. view the transaction details, we can go to the transactions tab bar here, and then we can filter out our transactions, and once we search we will get our transactions over here. And let's take a look at our servers running right now. There are 3 nodes running right now, all 3 are online. Let's look at our code to show you to have an understanding of all these nodes being run. All these nodes are running. So once we go offline with one node, that node will be offline over in the interface, showing that only 2 nodes will be running, as you can see. So this is a small summary of our distributed UI interface. Let's